I was planning to go in detail through the proofs of what we talked about last time, which is coming up with this canonical DR plan. Given a graph, how you come up with the canonical DR plan, given a graph that's independent in the corresponding dimensional rigidity matroid, why the canonical DR plan is automatically optimal. And then if in fact you have a sparsity matroid that or an oracle that determines maximal rigid subgraphs, then we actually have a polynomial time algorithm for finding this optimal DR plan. I wanted to go through those proofs, but I think that's probably not going to be doable in 50 minutes in any case. So I'm just going to put that off until we come back. And in the meantime, I also last time motivated how once we have the DR plan, how we go ahead and use the DR plan for solving, for getting a block triangular polynomial system and for solving it. So what I wanted to do is spend a little more time on that motivation, just to convince you that this picture that I had in the beginning is actually a viable picture. So in other words, what we had before, what we are trying to do is extend a kind of a simple situation that we had for the case of tree decomposable graphs. The graph is tree decomposable. We get the tree decomposition very quickly. And once we have, because you can do that using this paper by Fudos and Hoffman, or in general, I mean, they just sort of formalized it, but it was kind of hidden in the sort of very basic algorithms literature in computer science for a long time, which is basically, if you have something like this, it's basically biconnected, but not triconnected. You can very simply find these 3 points that separate these three into 3 components using any kind of depth first search or standard methods. And as a result of which you have the 3 parts. And then once you have it, and there are many ways of doing it, splitting into 3 parts. But the nice thing that Fudos and Hoffman prove is that it really doesn't matter which one of them you choose. You can choose any one of them you want. And all of them lead to the same, it's called the Church-Rosser property. So, so you start out, find these 3 vertices and split up into 3 components, keep doing this recursively. And so finding this tree decomposition is very quick. It's basically quadratic in this number of vertices. And then once you have the tree decomposition, you can get basically a triangular system of equations, polynomial equations with essentially one quadratic that you're solving at any time. So our goal is not exactly to get always one quadratic solving at any time. It could be some constant number of quadratics. The source of the complexity in general is the number of polynomial quadratic equations that you solve at any given, simultaneously at any given time. So in other words, the size of the block. And it's exponential in that. If that size of the block is constant, independent of the number of vertices of your original graph or the size of your original polynomial system, the size of your original polynomial system, the number of equations was the number of edges in the graph, number of variables was, some d times the number of vertices in the graph. So essentially, if your DR plan decomposition gives you a system where at any given time, the number of quadratics you're solving at simultaneously, which in other words, the size of the block is constant, independent of the size of the input, then you're home free. So complexity wise, that's what you're aiming for. Of course, later on, you can optimize, you can get that block to look good, ensure that the block also has low degree polynomials and whatnot. So in the tree decomposition case, you actually do get quadratic polynomials all the time. And the blocks are one or two, depending on how you think about it, whether you allow linears or not, okay? And what we want to do is just get a generalization of that to arbitrary graphs. The 3D composable graphs, as I said, is a very fixed, very small class of graphs. First of all, they're minimally rigid. And second of all, they are not tri-connected, three-connected. And so essentially, it reduces the class of graphs to a very small set. Even among 3D composable graphs, if you remove some edges, make them not minimally rigid, then, I had some examples here. So those types of graphs, these are essentially 3D composed. 3D composable modulo the fact that this cannot be decomposed at all except into edges, right? So this is a K33 here. But other than that, the way they are connected up, this is a 3D composable graph minus some edges. So it's essentially an under-constrained graph obtained from. So the usual method are not going to work to find the DR plan. So so already in that case, to find a DR, so the goal of the DR plan is to sort of generalize this idea of getting a decomposition towards the goal of finding these nice triangular systems if you generalize the graph. So essentially, you want to be able to generalize the graph in multiple ways. You don't necessarily want to only have minimally rigid graphs. So maybe if it is not minimally rigid, then you should get a decomposition into minimally rigids, which then further recursively decompose. And the goal is, after you get that, to get an automatic way of now getting a block triangular system here with low degree and low small size, all constant in proportional to the size of the original graph. And that's the goal. So I would not, the goal is not to sort of be very particular in the first stage when you're getting the canonical DR plan. The goal is to sort of minimize what we call the maximum fan-in, which, as we said, was the number of subsystems or subgraphs that need to be somehow combined to get the parent graph or the parent system. And that number is a rough gauge of how big this block and how complex the block that you're going to be solving at that stage is going to be. It's not an exact measure. You still have optimization that you can do after you have the DR plan to be able to get the, sort of the optimized block. You can do all kinds of elimination tricks, substitution of different new variables and all kinds of things, right? So what I was trying to do in the last lecture was, in the very end of the last lecture, was to give you a picture of what that latter optimization would look like, which means you have the DR plan, and now you're converting the DR plan into a block triangular system. And then, in that process, there's some optimization you can do. And I was going into that part. So what I was hoping to do today was to just walk through this process a little bit slower, so it's well motivated, this idea of why we want to minimize the maximum fan-in, and thereby this long proof that I'm going to go through to get the optimal DR plan is something that you will see the point of doing. So I was going to take Alex was the one who suggested to me to do a small example to even start with the 3D composable graphs, and then go from there to see how you get the triangular system. And then that sort of allows you to, us to go to the other example that we had with the 3-dimensional case, and talk about this idea of recombination and how that gives us the system here. So the process of starting with the DR plan, and at any given stage, sort of getting the solutions of the subsystem corresponding to a parent from the subsystems, solutions of the subsystems corresponding to the children, is called the recombination. So I just wanted to quickly give you some references. I'll put the links here when I make the slides put the slides in the Piazza, slide links in the Piazza. There are some this idea of decomposition and recombination in, as a graph theoretic way of solving it. So just to, before I go to this, I just forgot to say something. So this portion here, going from here to here is, or going from here to here, is purely based on graphs and matroids. That there's one algorithm doing this. And that's just, the proofs, underlying proofs saying, okay, this kind of DR plan exists and this kind of DR plan is optimal. And all of that is just based on graphs and matroids. The algorithm that will then, either using a sparsity matroid to determine rigidity or using an oracle that gives answers to rigidity to actually construct the DR plan, the algorithm, the proof of correctness and complexity of the algorithm are all just based on graphs. So this portion here, if you think about this, is all only just based on graphs and matroids. It's purely combinatorial. Then you've got this part here where you're now converting the DR plan into a system that you solve. Obviously that has, algebraic, you can solve it either algebraically or semi-numerically. It's quite a bit of just algebraic sort of elimination, elimination theory type of stuff. But I wanted to point out here that this optimization, once you have the optimal DR plan, so in other words, you've got optimized the fan-in, to convert a single recombination step, a node like this to that single recombination step, which means finding the solutions of the parent from the solutions of the child subsystems, that involves solving a system. And that's I'm representing this as this block. That obtaining an optimal form of that system in terms of algebraic complexity, that process itself has some combinatorial content. So this optimization of the recombination system that you solve, or put it another way, optimization of the algebraic complexity, by which I mean the number of equations and the degrees of those equations. So that optimization has in it a combinatorial piece. So although one might say, okay, this piece is all combinatorial and this piece is all algebraic, it's not quite the case. Going from the DR plan to a sort of an optimal recombination system, optimal in terms of algebraic complexity, which we define, it also has a combinatorial content to it. So once we come back 2 weeks later, I will spend the first period just explaining or proving that the canonical DR plan is optimal first, and secondly, give an algorithm, which we sketched previously, but I'm going to spend more time on it. No, we sketched the algorithm. I'm not going to go further into the algorithm, but then we'll prove that that algorithm will actually give us the canonical, or what we call the pseudo-sequential, which is equivalent to canonical DR plan. Okay, and that it takes, and its complexity is no more than V cubed or something. So that's the first thing we would do. And then the second part is we were going to spend some time talking about the combinatorics that are involved in optimizing the algebraic complexity of the block for a single recombination step. Okay, so that's the agenda. Now, to motivate this sort of hard work that we're going to be doing, I'm going to just go through the small examples. First, I'll do the small example of 3 decomposable graphs to go from the DR plan to the recombination to get the triangular system. And then we'll go redo the little example that we did in a hurry at the end of last lecture with the general canonical DR plan, a single recombination step of a general DR plan, and how we go from there to its block triangular system and what the optimization there entails. Okay, so so let's start with the simple example. Yes. New share. Okay, whiteboard share. Okay. Stop me at any time. I'm just going to go through this at a relaxed pace here. Okay. Okay. So, oh, I guess I turned it off. Okay. So let's take this simple tree decomposable graph. Before we do that, let's just, before we do this, even before that, even basic. So just suppose that all I'm given is a triangle. That's the very basic tree decomposable graph where each one of these guys is just an edge each. It's just one edge, and one edge. So, and say, and how do you write this down as a single quadratic in, you know, finding the positions of this? How do you write it down as a single quadratic? So let's just go through that exercise. So, so what is all given to us? There's the graph given to us, and then there are these distances given to us. So this, let's call this 0.1, 0.2, 0.3, and let's say this distance is given, this distance is given, and this distance is given. Okay. So what are our three equations? That the starting polynomial system looks like x1 minus x2 squared plus y1 minus y2 squared. I'm just going to keep, I've always debated whether d12 should already be a squared distance or should we keep it like this. Let's just keep it like this because people are more used to looking at just distances instead of squared distances, and there tends to be confusion because of that. So we'll just stick to this 2 minus x3 squared plus y2 minus y3 squared is d23 squared, and this one is d13 squared. And here we've got x1 minus x3 squared plus y1 minus y3 squared. Okay, so we've got three equations and we've got 6 unknowns. What happened to the remaining 3? So 3 equations. Somebody.
Pin them?
Yes. So essentially, the point is that we are only interested in solutions modulo rotations. So we want solutions, which means, you know, real values for the point coordinates, real point coordinates, real xi, yi, right? We want those, but we are only interested in those solutions modulo rotations and translations, because everything here is Euclidean, okay? Translations. And how many are there in 2 dimensions? So this is R2. So we've got 1 rotation and 2 translations. So essentially this point here, if there's an origin here, 0, 0, you know, so this point has been translated by something, then all of those, you know, so the same translation applies to all of them. So there are 2 translations. And then there's the rotation of the coordinate system. So basically you've got 1 rotation and 2 translations. Okay. So essentially to get rid of those, since we only want the solutions modulo rotations and translations, to get rid of them, simple trick that you apply is you simply say, okay, since I don't care about this translation anyway, let's just assume that this point is 0, 0. Okay, so x1 becomes 0 and y1 is also 0. Okay, so maybe I should have used a different color there. Okay, x1 is 0 and y1 is also 0. Okay. So we had x1 here and y1 here. Similarly, since we don't care about the rotation, x2 by default, you can simply put it on the x-axis. In other words, we don't care about the rotation of this x-axis. So basically you can put this point here at D12. And because we know the distance here is D12, just put it there. And then the y, since we're putting it on the x-axis, we can just make this D12 0. So our y values here, x2 is going to be D12. And your y2 is just going to be 0. Okay, so you can see here immediately this equation, basically, we have taken care of this equation basically by making these substitutions. So this equation is basically gone. So now you've got two equations in two unknowns, and you can modify that a little bit by, just thinking about this as, okay, there's the point. Basically, we need so the x2 and y2 and x1 and y1 are all gone. I can substitute these everywhere. So this guy's x2 is D12, y2 is 0, x1 is 0, y1 is 0. This seems to be two equations in two unknowns, which looks something like D12 minus x3 squared. It doesn't matter because it's a squared. I could have changed the order here. And then plus y3 squared equals D23 squared. And then you've got this x3 squared plus y3 squared equals D13 squared. We can manipulate this a little bit. And the way I think about the manipulation, and this is very general, you can do this, is not just specific. So here you've got, think of this as x3, and this guy is y3. So essentially what we're saying here is that, you can eliminate y3 because you can write y3 in two different ways. So basically you've got D13 minus x3 squared. So because you've got y3, basically you can eliminate it. So you just have D13 minus x3 squared. D13 minus x3 squared is y3, which can also be written as, sorry. I did this wrong, right? Yeah, D13 squared minus x3 squared. Yeah, so that's y3 squared. And you can also write it as D23 squared minus, D12 minus x2 squared. Okay. So you've got this one quadratic, x3, no, x2 is D12 minus x3 squared. Okay. So you've got this one quadratic in one variable. Basically. So essentially that's what you need to solve. Yeah?
Meera, here the quadratic terms cancel. You only get linear.
In this case, yeah, because everything is a quadratic, I guess. That's what you're saying. Oh, here?
Yeah.
Yeah, sure. You can just eliminate y3 squared and you simply get this. You're right. Yeah.
Yes, actually, then when you substitute back into
no, you do have
y
D1
equation, you get two solutions for the y.
Yeah, that's right. So there'll be one quadratic one way or the other. You can't get rid of it.
Mm-hmm.
Right? So,
right.
Okay. So, so essentially that's our system. I mean, so that's corresponding to this. Now, so this we have done for the very first triangle, but so for the moment, okay, before we even go to this example, let's consider the simple situation. Well, actually, I think I'm just going to use this page for a second. So instead of this, just think of this for a moment, even though that seems silly, just think of it for a moment as this graph. Instead of these three graphs here, I'm just going to have three triangles. Okay. This is a little bit silly because you can think about this, instead of thinking about it as three 3D composable in this way, you could have simply thought about it as, a Henneberg zero construction or whatever it is. And so you construct this triangle first, and then you construct this, and then construct this, and then construct this using the same idea that we did a moment ago, construction of a triangle. You could have done it that way. But for the moment, if you just think about it as a 3D composable graph, so you have this guy, and this guy. So the idea is that you solve one of them, you solve all three of them. So that's what the DR plan tells you. So for this, for example, the DR plan will looks like, the 3D composition, if you will, which we're going to generalize to the DR plan, will, split it up into these three. So let's call the whole thing G, and let's call these three guys G1, G2, and G3. So basically it'll start with G, split it up into G1, G2, G3, each sharing one vertex each, and then take G itself, each of these. So G1, G2, G3 will be again split into, say, a triangle and these two edges, right? So triangle and two edges, and then the triangle will be split into the three edges, which is the step that we just did, okay? And I'm just taking one step. We don't even need these extra triangles here, but let's say, suppose it looked like we thought about it this way, and these are the three. So then the corresponding G here would be G. This whole thing is G, and then these guys are G1, G2, G3. So we have G1, G2, G3, and then each of those is a triangle. So it has three edges. So the same thing here and same thing here. So the idea is to solve the three of them. And then once you have the solutions, to put them together. And in all cases, even in this case, if you have the solution to this, a solution to this, and in this case, let's say we took the solution which puts this point and this point on the opposite side. So you have found that length, and you have found that length, and you have found this length. And therefore now all it takes is to find a to position this point. That's all that's left to do in doing this recombination step. This recombination step just requires, since you already have the solution to G1, G2, and G3, and you're trying to get the solution to the whole thing, all it takes is to, find this triangle. So find this point. Once you find that point, you're done. So this step that we did just now is sufficient again to do that. So that's how the 3D composition works. So let's just work out the case. So I just want to point out what this recombination takes once you have the solution to this, and the solution to this, and the solution to this. Okay. So so once you have the solutions, the problem, as you can see, is that if you solve this separately, you have, in the same way, you have solve this triangle. Let's give these guys names. So let's say, let's call this guy P1, P2. I could have just done 1, 2, 3, 4, 5, 6. And if you had already done 2, 3, 5, right? So if you had solved 2, 3, 5, you would have placed 2, 3, 5. Let's say 2, 3, 5. You solve that triangle, you would have put 2 at 0, 0, and this point at whatever, D2, 3, 0. And you would have found the coordinates of 5 in the local coordinates. You think of it as a local coordinate system of this triangle, where you have placed 2 at the origin. So that's the solution that you will have for this triangle, and that's the solutions that you will have for this triangle. And that's the same in any one of these things. When you finish solving them, you'll have pinned the local coordinate system of that piece by pinning one point at the origin and another point on the x-axis somewhere. Okay, so that's, and you would have done the same thing for this, and you would have done the same thing for this. So let's take this example where we have done the single step. So each one of these triangles has been solved in this way, and all of them have such a solution where one of the points has been placed at 0, 0. The other point has been placed, let's say, on the x-axis somewhere, and the third point is the only one that you have solved for, really. So you've used one quadratic for this, one quadratic for this, one quadratic for this, and now you want to put them together, quote unquote. But what that means is to find the rotation and translation of the coordinate system of this thing and the coordinate system of this thing so that these points coincide, this point coincides, and that point coincides. Okay, so the recombination step, so to speak, this recombination step, or for that matter, that recombination step, any recombination step, where, as I pointed out in the tree decomposable case, every recombination step corresponds to solving another triangle, all of whose distances are known. But the solutions, quote unquote, for this have been expressed in its local coordinate system. Solutions for this have been expressed in this local coordinate system. So solving this triangle, so to speak, just corresponds to rotating, finding the rotations and translations of these two, what do you call it, triangles or subgraphs, so to speak, in such a way that these 2 points coincide, these 2 points coincide, and those 2 points coincide. You understand which I mean by 2 points. There's a point in this triangle corresponding to this point. There's a point in this triangle corresponding to that point. There's a point in this triangle corresponding to this point, and there's a point in this triangle corresponding to this point. So there are 2 points that need to coincide, 2 points that need to coincide, and 2 points that need to coincide. So you can think of this recombination system of solving this triangle, so to speak, equivalently as finding the rotations and translations of each of these pieces. You can always fix this to be wherever it was before, and such that these points, the coincidence constraints of the points is satisfied. Okay, so the 2 are equivalent. Thinking of this in the tree decomposable case, solving any recombination step, you can think of it as, you know, I know these distances, and therefore I want to place them in such a way that I know the position of this point, and then recompute the coordinates of these guys. The same thing as doing this. So they're identical. So I want to point, do a, motivate what I mean by this by just taking this little example. Okay, so let's just take the example we just did, right? So just for a triangle, this is sort of like the trivial case of what I'm talking about. The trivial case of thinking about solving, finding a polynomial, solving the quadratic system corresponding to a triangle. You can think about it as finding a rotation and translation of something to get some incidence constraints to be satisfied. Okay.
Can I ask a question before that?
Yeah.
So you said that when you're recombining, let's say you're recombining 2 subgraphs, you need at least 2 points to coincide in 2D, right? So is that something we keep in mind when we're doing the decomposition, that 2 things that need to be combined have to have at least 2 points in common?
This is not true. Look at this case. There are 3 things.
We are recombining 3 things there, but if you're just combining 2, if you just have 1 point among them, then it will not give you a unique position, right?
It's an under constraint system. So in that particular case that you're talking about, you would not have a DR plan that's a tree.
Okay. Mm-hmm.
Okay. So, but I think what you're saying is if the whole thing is minimally rigid,
yeah,
then if you have 2 subgraphs that are minimally rigid in it,
mm-hmm.
then they would necessarily have to coincide on 2 vertices.
Okay.
Right. And that was sort of incorporated in our definition of the canonical DR plan. So in other words, if we took, we had the 2 cases of the canonical. Let me continue with this, Rahul. I can come to that. I can recall the 2 cases of the canonical DR plan, which exactly reflect the 2 types of pairwise intersections between the subgraphs.
Okay.
Yeah.
Could I ask one question before we move on? It seems like there's some kind of magic that happens. As you're doing the recombination step, at each stage, it seems kind of clear how you're supposed to go ahead. But right at the very end, you've got, like, for instance, in this most complicated graph that you've got, right at the very end, you put this last piece in, and it has to match up in 2 spots, not just one. Why does it match up in the second spot? Like, the first spot we guarantee because we rotate it appropriately and translate the piece appropriately, but then it has to match up, like, with one of the other pieces.
I think maybe it wasn't clear what I was saying. So I was thinking about it in 2 different ways, right? The first way is to think about just, so I have already solved this, right? And I have solved this, which means I know this distance.
Yes.
I can compute that distance. Similarly, I can compute this distance. And I know that, so once I find that these 2 distances, then I can position this point using the same method that we did. Okay, so the point is known. So because we know that these 2 distances are what I got from the solution to this and solution to this, I know that I should be able to place this guy with that distance here, and same thing here.
I see. Okay.
Okay. And so now all it takes is to find whatever the rotation and translation that will put that, I'll have to
I see.
Change of basis. I have to do a change of basis for the solutions that I had for the X and Y coordinates for this guy and the X and Y coordinates for this guy.
That makes sense. So you first solve this kind of purple triangle problem, and then you patch the pieces on top of that.
Exactly. And I'm trying to say that the reason I'm doing this, thinking about this in this slightly more general way, is because by thinking about this in this slightly more general way, we can extend to general DR plans, not just the 3D composable ones. Okay. So if you think about it in the slightly more general way, what you're really doing here is, and I put the triangles here because that was the example I was going to do, but we can stay here if you want, okay? So I can just use the same picture. So this picture, you can think about it equivalently, as I said, as, either solving this pink triangle, I think I'm usually at another color. So either solving that pink triangle or just saying, okay, I've got a rigid body that I've placed here. And I have a second rigid body whose rotations and translations I have to find. And a third rigid body whose rotations and translations I have to find in such a way that these 2 points coincide, these 2 points coincide, and these 2 points coincide. Okay, so I can think of it as finding the rotations and translations, the orientation. So T, for any given rigid body Ri, I want to find the translation, the rotations, and same thing here, such that these incidents, now I've converted it into a set of incidence constraints between points. Okay, there's still a caveat here that some of these incidence constraints, each of these, you might think of it as I have to equate the x's and I have to equate the y's. Equate the x's, equate the y's, equate the x's, equate the y's. That seems like there are 6 of them. But really, because these distances are known, 3 of these 3 incidence constraints, of these 2 incidence constraints, only 1 is independent. And that's one of the things that we're going to talk about later, is how to get a well-constrained set of incidences, knowing that this distance is fixed, and this distance is the distance is actually given. So you don't have 6 independent incidence constraints. So anyway, that, yeah.
So just to make sure I'm thinking about this right, when you're taking 3 rigid bodies with these coincident vertices, this would correspond to a system of 8 equations, 2 quadratic, 6 linear, in 8 unknowns?
If you just think about it as 3 rigid bodies in 2 dimensions, you mean?
Yes. Yeah.
Well, you can sort of without.
So the 3 vertex coincidences are 6 linear equations.
That's right. X1 equal. I mean, X1's position in the first one is equal to the X1's position in the second one. Yeah, that kind of thing. Yeah.
Okay, and then 2 of the rigid bodies, you'll need a rotation. So you introduce maybe 2 variables whose sum of squares is 1.
That's right.
So that gives you 2 extra. You have 6 linear equations from the coincident vertices and 2 extra quadratics to handle a rotation.
Right.
Okay.
Okay. But then, as I said, several of the, because you fixed this position, right? Several of these linear ones just disappear.
Yeah, the linear ones will be really nice and easy.
Easy, yeah. Okay, yeah. So, so the reason I'm going through this crazy exercise, you say, oh, I just do the triangle and then I find the corresponding. The reason I'm going through this other way of thinking about it is because that can be generalized to anything. Okay, and that's what I rushed through last time. And I wanted to take, and Alex sort of made me aware that I had rushed through it. So I'm going to take a little longer to, go do that. So here, but let's just take our simple, just to go back to what we did, since so let me just draw this sort of 3 rigid body picture. R1, R2, R3. So this is all living in R2 for the moment, just in case I say, but it generalizes to any dimension really. So what we're saying, and it won't be exactly 3 things. It'll be, for higher R3, it'll be 4 things, each incident on 1 point, but there are more things, more possibilities will be there that they're incident on an edge and various other things, all within minimally rigid graphs. Okay, so for the moment, let's just stick to R2. So here we are, and we want to put this together. And the lazy thing that we did when we solved one of them, any one of them, the lazy thing that we did is we just said this is 0, 0. And this thing is whatever, D, if you had 1 and 2, so we said D1, 2, 0. But let's say because, these are floating around and really you don't have you cannot really do that to all 3 of them. Think of it that way. So what you really, if you didn't want to introduce sines and cosines in the beginning, what you should have done is just say, okay, I'm not going to do that. I'm just going to call this x1, y1 and x2, y2. And of course, that's your familiar equation. So that means these are connected by a very familiar equation, which is that x1 minus x2 squared plus y1 minus y2 squared is d12 squared. Okay. And so now if you eventually, so what we're essentially saying is that we don't know where x1, y1 is in relation to, so there's a translation here, and we don't know how this might be rotated in general. So there's that rotation. So there are 2 translational variables here, and there's a rotational variable there. That will take us from 0, 0, d12, 0 to x1, y1, x2, y2, plus, of course, the fact that we know that one of the distances is this d12. So, that's known. So if you think about it that way, you can, think of it as rotation and translation. You can simply leave the translation as x1, y1. Those are my translational variables, x1, y1. And now let me think of this other thing as a rotational variable because this distance is fixed. I can simply set, make the substitution, and this I can do always, right? I can always make this substitution. By always, I mean, it doesn't matter what dimension I'm in. Okay, so x2 squared minus y1 minus y2 squared is just call it, or this we know happens to be D12 squared. Just call it, C2 squared, just the cosine of the rotation angle. And you can also make the other one, y1 minus y2 squared divided by D12 squared as the cos, and then simply set C2 squared plus S2 squared equals 1, right? So if you do this, then the process that you went through to, so basically you will, because of this, also get that x1 minus x2 squared is going to be D12 squared times C2 squared and y1 minus y2 squared. I mean, I could have removed the squares, but I'm just leaving it there because that's what falls out of this. So you basically get D12 squared times S2 squared. Okay, so essentially you get the the variables, the second variable of x2 and y2, the coordinates of the second point. The coordinates of the first point are the translate. We're going to leave it. The coordinates of the second point you can simply obtain directly from these two other variables. So basically you're changed x2, y2 into these two other variables. So that's essentially what's going on. What you did in the beginning, the pinning of each one of these into its local coordinate system by setting one of the variables to 0 and the other one to be something. Instead, if you had just done what we just did, then you have for each one of these, so for R3, you'll have a C3 and a S3 and a translate for one of the points, translates for one of the points, and the same thing for this one. So again, you'll have a C2 and an R2, S2 and a translate. So essentially, you have just rewritten the equations in this manner. That's all there is. Okay, so now I think we can go to that second part of the second hour that I had last time. I'll save this. Okay, and and take our go through that. Okay, so now we're going to R3. So you have to do a little your imagination has to now move to R3. So what we had here, and the clusters are basically, this is one recombination step. We're concentrating, just like we did a moment ago, just on one recombination step. In that recombination step, in this case, we happen to have in the first case, just think of the first case, we just have the clusters C1, C2, and C3. Okay. So it's one possible way to think about the recombination step corresponding to one parent with its children. Okay, so it's the parent and its children will look like this in what is called the canonical DR plan, which essentially has all the maximal proper subgraphs that are rigid. And what I have drawn here, C1, C2, all the way through C7 are all of the possible children of that parent. I mean, all of the children of that parent in this canonical structure. And we are now about to do one recombination step. And I'm going to point out to you that, the DR plan will give you this canonical decomposition. And there is still work to be done when you're doing each recombination step to sort of find the best way to write that system. Okay, so first we're going to do the sort of dumb way to write the system, and which is almost a direct mirror of what I did a moment ago for the triangle decomposable case. Okay, so what it's going to do is for each of the it's going to represent the X coordinate in the coordinate system of that particular child, which I call CI, child subgraph. And this is what I'm going to call that. So for a given point A, XACCI is the coordinates of that point, the 3 coordinates of that point in the local coordinate system of the child in which it belongs. And as I said, there are some points that are going to belong in 2 children, which means it'll be clear, even though it says A, because I'm looking at that particular child, you're going to have a separate coordinate for that. Okay, so XACC, so this one, I think this is a mistake here. So XACI would be the coordinates of A in local coordinate system. And this is the coordinates of A parameterized in C's coordinate system. Okay, so there's a slight difference here, but we'll come to that later. Let's talk about that later. So now what I call the unoptimized algebraic system, which is what we basically did just now. You can take any subset of children which cover all the vertices and place them solve for their rotations and translations, so their corresponding SICI, whatever, in such a way that incidences and potentially certain distances have to be satisfied. This is one way to do it. Otherwise, you could have, if you had done it exactly the way I talked about, you would then use essentially not just C1, C2, C3, but you would also in addition use C5, C6, and C7, and make incidences that say that the point H in C2 is the same as the point H in C7, and so forth. You would have done all of them. But in general, it is sufficient to take a set of children whose set of vertices cover the set of vertices of the entire graph, and then have a combination of incidence constraints and distance constraints, and the distance constraints being those edges that have been left out. So when I say covering set here, I mean covering set of the vertices. So if I take covering set of the vertices, and then the edges that have been left out from this covering set are then added as constraints that need to be solved in the recombination system. So they set the coordinate system of C to be one of the child clusters, which is the home cluster. And the simple case, we're only going to take C1, C2, C3, and we're going to take C1 to be the home cluster. So this would be sort of the dumb way in which we did. A moment ago, we had 3 clusters and we just took any one of them and set them as the home cluster. So home cluster means that's the coordinate system in which everything is going to be eventually expressed. Okay, so so get C2 and C3's position and orientation within C's coordinate system using a composite 3D rotation matrix and a translation vector T. Okay, so in the 2-dimensional case, we just had one angle and a translation, 2 translations. In this case, you'll have 3 translation because the first point will be some x1, y1. The first point in a given cluster will have 3 coordinates. That's the translation of that cluster. And it will have, and I'm here in this case simply going to call it TC1, TC2, sorry, TCI. So TCI is the XCI, YCI, and ZCI, right? And the rotation matrix. So basically the rotation matrix that will give you the new positions of any given X, Y in terms of the old positions. Just like we wrote down a moment ago, the X2, Y2, I guess I should just go back here. So just like we wrote X2 now in terms of the rotations here, we can just think of it as a matrix that would then it's a linear transformation that takes the old coordinate system, all the points in the old in their old bases, express that in the new bases after the rotation and translation. That's a matrix, and you can just think of this as a matrix equation, and that's what we've done here. Okay. So you can now write the any new so the positions in the of a given point in the new coordinate system can be written by just applying this rotation matrix to the positions of the point in the old coordinate system, okay, in its original coordinate system in which you solved it. So basically you have in 3 dimensions, of course, you have 3 cosines and 3 sines, and then of course you have the SI plus CI squared equals 1, 3 of them, instead of just 1 as you had in the 2-dimensional case. So if you did that, your unoptimized algebraic system, which is again just for this 1 recombination step, again remember each recombination step corresponds to 1 block of the larger system that you're solving. Once you solve it, all the points, all the variables here are now going to become, you know, sort of fixed. And the only variables that are going to be left are going to be the rotations and translations of the entire system to be placed in the next recombination step in relation to the other, you know, others that are also children of the grandparent. Okay. So, so if you go here, so you have 6 active constraints by 6 constraints. Oh, remember that we have these 3 distance constraints. So once we took C1, C2, C3, we still have, it didn't cover these constraints. So this have to be established. So instead of an incidence, you know, we actually have to say that the distance between D, which belongs to this cluster, and I that belongs to this cluster is something. And of course, you have the 3 incidence constraints that says that the A in this cluster is equal to the A in this cluster, C in this cluster is equal to the C in this cluster, and B here is equal to the B here. So you've got 6 incidences and 3 distances. So that's what it says here. So 6 active constraints, 3 distances of this type, and it says 3 overlap constraints. These are incidences, but the incidences are really 9, because the 3 incidences now become 9 of these, because 1 for each of the 3 coordinates. So altogether, you end up with 12 polynomial equations in 12 variables. A lot of them are, of course, these linear ones. They look linear, but if you remember, this is the coordinates that are have to be multiplied by the rotation and translation matrices. So each of these will really be, all of these will just be in the variables, SIs and CIs variables. So the 3 distance constraints will have degree 6 because each of these variables themselves have potentially, you know, combinations of sines and cosines, like things like, you know, they have potentially S1, C2, C3, things like this. So as a result of which each of these might have degree 3, and then you square that, it becomes degree 6. And, and if you can work a little harder and use quaternions for the incidence, so you'll end up with 8 equations of degree 4, okay? So that's the unoptimized algebraic. Let's forget about this last bit, okay? So just think of it as 12 equations in 12 variables, and each could have degree 6. The linear ones, of course, have degree 3. The quadratic ones will end up with degree 6. So if you, now this tells us that if you did it the way that we did it for 3 decomposable graphs, which is simply solve the 3 rigid bodies and do the obvious incidence and distance constraints between them in order to place their relative orientation with respect to each other, this is what will happen. But then if you do it a little bit better, and just give me a few minutes, we went through this once, so I can do this very quickly in about a minute or 2. So just think of the central. So instead of taking sort of like a minimal set that covers all the vertices, you take another set, and that requires, I will show later, that requires solving another optimization, combinatorial optimization problem, which is to find this set. And why did we find that set? Because if we did that, then because these are adjacent on an edge, there's only one rotation to be solved for each of these three clusters. So there's only one rotation angle, and there are of course three incidences, right? So if you took this as a home, and so again, this is showing two different possibilities. If you took this as a home cluster, then you have the two incidences here, and you now have a rotation of a 3D object around a point. And, or sorry, you can fix this and have a 3D rotation about a point, and that itself corresponds to two rotations, and then you have one incidence constraint. You could do it that way. Or you could simply say, okay, this, I just think of this as my home cluster, and then each of these is related to it using just a 1D rotation, and be done with that, okay? And so, and in general, you know, you may not know these, these may not be edges in the original graph. So what this is saying is that these need not have been edges in the original graph. This, you know, this could have been a non-edge. This could have been AB could have been a non-edge, AC could have been a non-edge, as we had in this case, in the original. So in this case, for example, this was a non-edge, 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 but it doesn't matter. Those distances are known because you've solved this and solved this and solved this. So what this is saying is that, what this is saying in this picture here is that you don't, you know, this thing in the middle need not have been a subgraph that's rigid, right? As long as we know this, the length here and this length here and this length here from having solved this, this, and this, you can use that essentially as a rigidified, so to speak, triple of vertices A, B, and C, okay? So you can simply use that as though it were a rigid subgraph in the middle. So that's what you do. So the second thing is use C1, C2, C3, and C4. And C4 may or may not have been a rigid subgraph of the original graph. So in other words, it may not have been in the canonical decomposition at all. You could still use it as an optimized way to actually take the recombination step in the DR plan and get an optimized algebraic system, okay? So so you use the C4 as the home cluster, and then you simply use the sine and cosine of the angles, those three angles that are shown here, these three angles, right? We're not doing this. This is a silly way to do it, to use this as a home cluster and use like a 3D rotation angle about this point. This is not being used. We're just using this one. And if you do it that way, we end up, to cut a long story short, we end up with 6 constraints and 6 variables, and all the constraints are quadratic. Okay, and so, and in the, it says compare with degree 4, but in that comparison with degree 4 is already doing some non-traditional stuff here with quaternions that got this thing down to degree 4, right? So in general, it was degree 6. So now we have also done something totally automatizable. And I'll show you that this optimization step that I just did of picking this as the home cluster is also a totally automatizable step. And we can now have decreased the algebraic complexity. So, so there's some work to be done. I mean, as you can see, it's not quite clear how this can always be done. And that's what then the second set of lectures after the break will be about. Okay, hopefully that made it a little clearer, Alex.
Yeah, that was great. Thank you.
Okay.
You could, of course, just start with the original graph and have just all quadratics, all degree 2, but just many equations and variables, right?
No, the problem is that's not the thing. How do you solve a it's an untriangularized system. That's the problem.
Yeah, like you could solve it with homotopy continuation.
Yeah, you could do homotopy continuation, and that's that typical complexity of that is double exponential in the number of equations that have to be solved simultaneously. Okay, so that's with Grobner, the complexity of all of those.
No, not Grobner basis.
No, even Grobner, anyone in the end, if you're going to find all the solutions, it's equivalent to having done Grobner basis. Even with homotopy continuation, if you want to find all the solutions, it's the same complexity. It's not any better, complexity-wise.
Okay.
Yeah. So if you want to solve, so the point here is,
you don't get the actual solutions exactly. You get numerical approximations.
You get numerical approximations. I understand that, but the point I'm not focusing on that point. I'm focusing on the point that you have to find all the solutions.
Okay.
Okay. So Bertini and all this stuff, I mean, initially in the homotopy continuation methods, which are semi-numeric methods, had to struggle with how do we ensure that we really do find all the solutions. But then now apparently they're pretty good at that. But my point is, no matter how you do it, whether you do it symbolically or numerically or semi-numerically or whatever, if you're going to find all the solutions, you're essentially doing something equivalent, whichever way you do it. And the complexities are the same. The only way in which you can defeat the complexity is if you can minimize the number of equations that you solve simultaneously.
Which is why this block triangularization.
Exactly, exactly. So, and once you have minimized the number you solve simultaneously, which is what the DR plan gives you, you still have optimization to do to actually reduce the degree and things like that, and the exact number. So the DR plan tells you there is a rough number of this equations that you have to solve simultaneously, but you can still optimize exactly what the proportionality there is, how many exactly, what factor of the DR plan fan in size you can actually eventually achieve in terms of the size of your system and the degrees and so forth. So that's the second part. So that's what we're going to do next, maybe 2 weeks. Okay, so the combinatorial part, how to find the DR plan. Second part, what is the combinatorial part in optimizing the algebraic complexity? And then we'll actually do the algebraic, the algebraic part itself.